record this?
I'm recording now.
You're recording now. Okay, cool. Okay, welcome everyone. It is our pleasure to welcome Koji Hashimoto, who's going to be speaking to us today. And I'll let him get started. Thank you very much.
All right, so let me share my screen again. I hope you can see this.
Yes.
Okay, so if there is any problem, please just stop me or please give me any question or discussion. So I'd like to thank Jeff and Nathan and all the people in Cape Town for inviting me to this opportunity. It's Friday night in Japan, so most of my collaborators are now enjoying dinner. But some kindly joined, Kunyon and Ryota and Norihiro. I'd like to talk about a summary of my papers written first with Keiju Murata and Yoshi-san about quantum billiard. And then I'll go on to coupled harmonic oscillator analysis done with my students, Akutagawa and Sasaki and Ryota Watanabe. And then finally, I'll describe my recent paper written with Kunyon and Kyonbon and Ryota. So all of these are kind of related to each other. And my final goal is this. Yeah. So the question is as follows. So suppose you are given some quantum mechanical system. It could be just one particle quantum mechanics or many body quantum mechanics. And from that, the given quantum mechanics, can you tell whether it has a gravity dual or not? Okay. So normally this kind of question is not asked. The reason is that in ADS CFT correspondence, in ADS side is gravity description, and CFT side is kind of quantum mechanics. And what is normally done is that for a given gravity system, you compute some things, and using ADS CFT dictionary, you say that this is a CFT result. Okay. So since the gravity part is classical and it's very easy to compute, so in this sense, ADS CFT is starting with the gravity part, then compute or tell something about quantum part, quantum counterpart, which is CFT. But to understand ADS CFT better, we should answer the opposite question, inverse question. So once you're given some quantum mechanics, then can you tell whether it has a gravity dual or not? And I think this OTOC is one of the best tools to actually distinguish or discriminate whether you can have some gravity dual allowed or not. And as you, I think all of you know, if this special OTOC of quantum mechanical observables grows exponentially and this Lyapunov exponent is given by the temperature, then we can say that it's a black hole horizon behavior. So at least it satisfies a necessary condition for this quantum mechanics to have a gravity dual. So in this sense, we need to sharpen this kind of conjecture, and we need to develop some ways to calculate OTOC for generic quantum mechanics. And here I draw one table, which is a kind of summary of this talk. So there are two notions called scrambling and chaos. And until recently, these two notions are quite confusedly used. So in this talk, I'd like to distinguish these two notions. And so here I describe various quantum mechanical systems, harmonic oscillators, quantum billiards, and coupled harmonic oscillators, and inverted harmonic oscillators. And depending on what kind of quantum mechanics you start with, so all of these are one particle quantum mechanics. So it's very simple and it's very standard, and it's a standard toolkit. And I checked and studied the OTOC. And the exponential growth of ODOC is now terminologically defined as scrambling. So scrambling means that your ODOC is exponentially growing. On the other hand, chaos means different. Chaos does not necessarily mean exponential growth of ODOC. So here, the definition of chaos is, in quantum sense, it's a Wigner distribution of level spacings, statistics. Or if you go to classical chaos, then that is the standard classical chaos. So here I mean quantum chaos. So this means that your energy level spacings follow Wigner distribution rather than Poisson distribution. So in this way, the definitions of these two are different. And what is relevant for us is whether it has a gravity dual or not. And that is directly related to this exponential growth of ODOC. So it's scrambling rather than chaos. And as you can see from this table, in fact, for different quantum mechanics, each of them has different features about scrambling and chaos. For example, harmonic oscillator, of course, it doesn't scramble and it doesn't have chaos. But if you have a coupled harmonic oscillator in a nice way, then it has both scrambling and chaos. And quantum billiard has quantum chaos, but it doesn't have scrambling. On the other hand, inverted harmonic oscillator is scrambled. However, it doesn't show quantum chaos. So in this way, we have to be a little bit careful about what we talk about a gravity dual. So as a summary, I can say that you need to check the exponential growth of ODOC first. And that is called scrambling here and not chaos. Do you have any question? Is this crystal clear? Good. Okay.
Sorry, Koji. I have a question.
Yeah, please. Yeah,
perhaps
please.
I'm shooting the gun, and you might discuss this a little later. But so my question is, how much is this a statement of what you're using to probe these properties of the system?
So
for example, let me clarify maybe a little bit what I mean. So you're probably aware of this work by the Leiden group, Konrad Schalm and Jan Zanen and people on the operator thermalization hypothesis. So their statement is, if you use composite operators, even free theories scramble in some sense.
Yeah. So that's the scrambling is of course different from this definition here, right?
Yes.
What? Yeah. So I think so at least there is a confusion about how we use the word scrambling and chaos.
Yes.
And I think the first and the popular definition of scrambling is about just scrambling time. And scrambling time in gravity picture is very clear, right? So you perturb the horizon and it spreads all over the horizon, the whole of the horizon. And that is called scrambling time. But now we extend this notion to quantum mechanical systems, which is a dual of this gravity system. So I will not talk about anything about scrambling time here. But here just I follow the definition of scrambling as an exponential growth of ODOC. So I'm not sure whether this definition of terminology actually continues to be used in our community. But since this exponential growth of ODOC is the best way to actually discriminate whether it allows a gravity dual or not. So I think this is a good terminology to use. And about your question, I think I have no idea how these are related. So at least in my case, this ODOC growth will never happen for free field theory. Yeah. Shall we discuss more later?
Yes, no, thank you very much. I appreciate that. There's a question from Nava Gadam that Berry and Keating showed that there's a boundary condition, that there exist boundary conditions that one can impose on the inverted harmonic oscillator that result in quantum chaotic spectrum. Do you have any comments on that?
Sure. Yes. I think if you actually change the boundary condition in such a way that, for example, if you allow time-dependent boundary condition, like a kicking with some random sequence, then of course chaos will show up. However, here I just mean the fixed boundary condition, like a hard wall or a soft wall, and I just put a one-dimensional inverted harmonic oscillator in it. So in this limited situation, there is no cause. But thank you. Yes, it's true that even in one-dimensional system, if you have kicking, then there is a chaos. I think so. Is that a point of the person who made the question?
Yes. Yes. Thank you.
Yeah. So in this talk, I will not talk about those time-dependent boundary conditions, although that's very interesting. Okay, so let me go to section 1, in which I'd like to make a review of why this ODOC is important. And this section would be almost obvious to many of you. However, to motivate you for this 1 hour, I'd like to talk about it. Okay, so first, I introduce a definition of chaos in classical systems. And then example of stadium billiard is introduced so that later I'd like to quantize it. And then I'll discuss quantum analog of this Lyapunov exponent in classical chaos is ODOC. And there is a famous bound about ODOC and Lyapunov exponent. And I'd like to relate it to black hole horizon. So 1 slide for each topic. So the definition of classical chaos is as follows. If I read it literally, it's a non-periodic bounded orbits sensitive to initial conditions in nonlinear deterministic dynamical systems. So you need to have a bounded system, and that's good for quantizing it. Since if you have an infinite system, then you have a continuous spectrum. So first you need to regularize it. And in classical chaos, there are 2 ways to see the chaos. The one is so-called Poincare section. So suppose that this is a phase space of classical system. So if it is a 1-dimensional system, then phase space is 2-dimensional. If it is a 2-dimensional classical system, then phase space is 4-dimensional. So this picture is a kind of 3-dimensional phase space. And then this line indicates the time evolution of the system. So it started here and then goes in this way. And if you consider a section of this phase space and then look at how this time evolution intersect with this section, then it plots some points. And if these points are scattered, then you say that it's chaotic. If these points are regularly ordered, then it's not chaos. And more quantitative exponent is called Lyapunov exponent. And suppose you have 2 orbits in phase space, and you put a very small difference in between these 2 starting points. Then after time t, if the distance of these 2 orbits exponentially grows like this in phase space, then this L is called Lyapunov exponent. Okay, so in the case of stadium billiard, for example, this is the popular stadium billiard with the 2 parameters, R and A. A is for this parallel part, and R is the for radius of this circular part. So if A is infinite, then this is integrable. However, if A is finite and R is finite, then this is non-integrable and known to be chaotic. For example, if you plot Poincare section in a certain way, so if you're interested in, I can tell you how I chose the section. Then, you get this scattered plot. So it shows chaos. And in fact, numerically, you can evaluate the Lyapunov exponent. And this is the result. So it is plotted as a function of A over R. So if A over R is 0, then Lyapunov exponent is 0. The reason is that when A over R is 0, then it means that R is infinite and A is 0. So stadium is circular. And circular system, billiard, is non-chaotic. However, if A and R are non-zero and finite, then it shows positive Lyapunov coefficient. And that means exponential growth of the distance between these two initial conditions. Okay, so this is a story about the classical chaos. So how about quantum case? So the standard way to argue this is to introduce ODOC. So although Schrödinger equation is linear, how can we actually measure quantum nature, a chaos of quantized systems? The solution is ODOC, and it was argued in this way. So consider a correlator which is ordered not in time order, like x of t, p of 0, x of t, and p of 0. So this x and p are chosen in such a way that if you take a classical limit h bar goes to 0, then it is identical to this expression, where differentiation with respect to x of 0 means you have operation of commutator with p of 0. So although this is not a commutator, so commutation relation actually is it has a subtle issue. However, generically it doesn't give you much effect. So if this exponential grows, then you say that this exponential grows, and the exponential growth of this thing actually means with a very small differentiation with respect to the initial condition grows exponentially after time t. So this is a quantum counterpart of the notion of Lyapunov growth. So we are going to evaluate this. And as all of you knows, there is a famous conjecture about the Lyapunov coefficient. And Maldacena, Shenkan, and Stanford, in their famous paper in 2015, they argued that there is an upper bound for this Lyapunov exponent for a specially ordered thermal ODOC. So their ODOC has a very special shape, and also it applies to large N theories. So it's almost a semi-classical bound, and also specialized to a particular ODOC. However, there is an indication that this bound will be true for more general ODOC. So even maybe in a different definition of ODOC, this may be true. And the reason is that since some large N theories like SYK models have gravity duals, and in gravity duals there is a very general argument that ODOC should grow with the exponent which is equal to temperature. So this bound was suggested from ADS-CFT with black holes, and renowned work by Kitaev showed that this SYK model saturates the bound. And there are many works following this Kitaev's proposal, and including Jeff's very nice work about Suji generalization of SYK. There is a big development about how to evaluate 4-point correlators and also ODOCs with this generalized SYK model. And people calculated the Lyapunov exponent and see this saturation. In addition to those important developments, what I like to tell is that this bound or saturation can be used as an indicator of having a gravity dual for given quantum mechanics. So my research and also this talk is based on that kind of viewpoint. So before closing this section 1, I'd like to briefly tell you why gravity dual can be seen in that way. So there are two arguments. One famous and initiating argument is given by Shenkan and Stanford in 2013. It was about shockwave delay. although for me, this paper is very difficult to understand, and still I have to confess that I don't understand it very well. However, in later papers, like this one by Fairinde, so they argued using 2D dilaton gravity very, very clearly. And the argument is as follows. So it's very clear. So first, so this is a Penrose diagram of asymptotically ADS black hole in any dimension. And here, dashed line is the horizon of the eternal black hole. And now consider bringing in some shock wave from the asymptotic boundary into the black hole. And then consider some waves coming out and observe it at time t2. So the shock wave is coming in at time t1, and we observe at time t2. And whether you actually put this energy in or not, depending on whether you put in this energy or not, in fact, the particle reaches this boundary, the time is t2, this t2 may differ. And the difference depends on what kind of energy you put in, and also the horizon behavior. And in fact, it is very easy to compute this delta T2, whether you actually put in energy or not. So the outgoing wave has a time difference delta T2, and that is computed to be proportional to delta E. However, it is exponentially sensitive to T2 minus T1. And the proportionality condition coefficient is given by 2 pi T, and that is determined by surface gravity, the Hawking temperature. So in this way, exponential growth and sensitivity can be seen by shock wave delay. And this is, and since this argument actually does not depend on any dimensionality and any kind of black hole, and the point is that it actually depends only on this 2 pi T, which is Hawking temperature. So we may roughly be allowed to argue that this 2 pi T saturation of the Lyapunov coefficient is an indication of the horizon behavior. That is very good about ADS-CFT, since in ADS-CFT we haven't reached any conclusion about how we derive ADS-CFT correspondence. So to explore more, we have to look at many examples of quantum mechanics and gravity. And also we have to discriminate whether a given quantum mechanics has a gravity door or not, right? So in that sense, so this criteria is very sharp and clear. So if you give me quantum mechanics, then I compute OTOC. And if it actually saturates this Lyapunov bound, 2 pi T, then we can say that it satisfies at least a necessary condition to have a gravity door. And also this 2 pi T can appear in a very nice way if you look closely at the near horizon classical behavior. And this is done in collaboration with Norihiro, who is here. We look at the particle motion near the horizon. So suppose there is a horizon and there is a particle which is moving near the horizon. If you don't do anything, then of course particle will go into the black hole horizon, and that's it. So if I want to probe the near horizon behavior, then you have to pull that particle away from the horizon in the opposite direction so that it stays around the black hole. It could be some, for example, electromagnetic force or anything. And if you consider such a particle motion near the black hole horizon, then actually you see that there is a top of the hill behavior for this particle probing near the black hole horizon. And when this separatrix is very close to the black hole horizon, then in fact, the curvature here is always given by 2 pi T, whatever the force you pull the particle. So this means that there is a universal behavior of separatrix near the black hole horizon. And of course, if you solve this equation, so effective Lagrangian, so if this solve the equation of motion, then it exponentially grows and the coefficient is 2 pi T. So this means that even for a very simple particle motion near the black hole horizon, can actually probe this 2 pi t as a Lyapunov exponent. So this is the end of my introduction. So I wanted to emphasize 2 things. One is that once you have a horizon with Hawking temperature T, then there is a universal mechanism of elongating the time difference by exponential function. And that exponent is 2 pi t. And second thing is that with using this, we can discriminate whether a given quantum mechanics has a gravity dual or not. So this is my viewpoint. So you may have some different viewpoint, and you may have some objection to my viewpoint. But yeah, so anytime you ask me a question. So I finished my introduction to quantum mechanics and OTOC. So let me go with one example by example. So first, let me describe harmonic oscillator and billiard. And now I have several topics which I want to discuss. So first, I'll show you how to compute ODOCs, and then discuss what the result for harmonic oscillators and also billiards. And the summary table is here. So billiard doesn't show scrambling, unfortunately. However, of course, it is chaotic. So in this sense, even though you quantize a chaotic system, it does not necessarily show scrambling. And we, of course, argue that scrambling is the necessary condition for having a gravity dual. So from this criteria, quantum billiard doesn't have a gravity dual. Okay. So each topic has one slide for each. So one by one, I'll go. So first, I'll tell you how to compute ODOCs in generic quantum mechanics. And then we go to quantum billiards. And I'll show you results for micro-canonical ODOCs and thermal ODOCs. And then I'll show you universal maximum values observed in ODOCs of quantum billiards. And then I'll conclude with no exponential growth in stadium billiards. So our definition of micro-canonical ODOC is quite simple. So N is the energy eigenstates, Nth energy eigenstate. And X of t is the Heisenberg operator, which has time t. And P is just P of 0 at time 0. And I consider X, T, and P commutator squared. That should correspond to the a classical exponential growth of the difference of the initial conditions. And the thermal ODOC is simply defined in this way. It is exponential minus beta En, where beta is the inverse temperature, and En is the nth energy eigenstate, eigenvalue. And CNT is the micro-canonical ODOC, which is defined here. So this is the very standard definition of thermal observables made out of micro-canonical observables. But please note that this definition does not follow Maldaceno's definition for ODOC, where they actually split this exponential function into 4 parts and stick them inside these 4 operators. So those are kind of a bit different. However, we believe that the most of the things can be captured with this standard thermal observable. So we are going to use it. And in fact, it's easy to check Maldaceno, Schenker, Stanford's definition for ODOC. So step 1 is, so there are 2 steps to evaluate thermal ODOC. The first step is to actually evaluate this one by inserting this 4 Hilbert space identity operator into here, and then define Bmn of t as a matrix element of this commutator. And this, its squared, gives you the micro-canonical ODOC. And then using this B, you can actually compute this CN and the resultantly this CD, thermal ODOC. And this BN is, in fact, since this is a Hashimoto operator, you can bring this to the Schrödinger kind of operator by using exponent, the time evolution operator. And then you have this expression. So this is a really explicit expression. So the resultant expression only needs matrix element for X and P operators. So you just substitute them, divide them, substitute them, and then compute ODOC. So for one particle quantum mechanics in any dimension, it's very easy. So here is a result of a harmonic oscillator. So omega is the frequency, and energy eigenvalues are this. The resultant ODOC is, in fact, independent of the energy label n. It's just a cosine squared. And thermal ODOC is, again, independent of the temperature. And it's recursive. The system is completely dictated by this frequency omega. And even ODOC and thermal ODOC comes back to the original value after the period. And also, you can see similar behavior for particle in 1D box. So this is a 1D box, and energy is n squared rather than n. And ODOC can be obtained only by numerically, but you can get it. And for quantum billiard, the computation is again easy. You have this kind of energy eigenvalues for labeled by n, the integer. This is the wave function squared for, say, n is equal to 1, 2, 7, 50, 200, and 400. And it looks periodic. However, if you go higher energies, then the behavior near this part look non-periodic. So this is an indication of chaos. And the computation is quite straightforward. So here is a result of micro-canonical ODOC for 3 systems. The one is a particle in a box, one-dimensional particle in a box. The second one is circular billiard. And the third one is stadium billiard. And as you can see, this first example of particle in a box, the micro-canonical ODOC comes back to 0, and it's periodic. And then what about the circular billiard? This is in fact it's integrable, so there is no chaos classically. And if you look at this micro-canonical ODOC, then it does not come back to the original value. So it's not periodic in time. So it's non-recursive. And stadium billiard look like this. Again, it does not come to the original point. It's not periodic. So chaotic example, so if you approach from here to here, then chaotic example looked a little bit smoother and non-recursive. However, one point is that although circular billiard is integrable, there is no clear distinction between these two. So both of them has a kind of a smooth, well, you would say that this is more zigzag compared to stadium, but it's kind of subtle since there is no periodic behavior for circular billiard. So it's subtle. The reason why circular billiard doesn't have a periodic behavior is that if you look at the energy eigenvalues, they are non-commensurable. Particle in a box has a very nice commensurable energy eigenvalues. However, circular billiard doesn't have it. So because of that, there is no periodicity behavior here. However, they are integrable. So even at this point, we see some subtlety in seeing or distinguishing chaotic from non-chaotic examples. And we are going to the jungles. So here is the result of thermal ODOC. So given a temperature, we can compute thermal ODOC. And again, particle in a box is periodic. Circular billiard is not periodic. And serial billiard is not periodic. And interestingly, stadium billiard has very nice flat behavior around here. So it looks like it saturates to a constant. So one may argue that this constancy may be seen as a chaotic nature of quantum systems. However, if you look at circular billiard, then you would also say that this is almost flat. So numerically speaking, the distinction between these two is very difficult. So let's look at this maximum value of ODOC for stadium billiard, and we may argue whether we can actually distinguish this one and that one. Okay. So in fact, there is a physical interpretation of this maximum or asymptotic value of thermal ODOC. That is this. Intuitively, asymptotically, this thermal ODOC may be described by typical momentum squared times typical size squared. And this expression is was already written in Madison and Schenker-Stanford's paper, the introduction. The reason is that the definition of this ODOC is given just by two x's and two p's come together, right? And if you wait long enough, then the correlation between those two would disappear. So basically it would be equal to x squared times p squared. So that's an intuitive picture. And in our case of stadium billiard, the typical size is of course like a plus r squared. A is the length of the parallel part of the stadium, and r is the radius of the radial, the circular part of the stadium. So it's roughly a plus r, and the system size is a plus r. And also, what is typical momentum? The typical momentum is given by typical energy, and typical energy is given by temperature. And since this is a non-relativistic system, energy is equal to p squared divided by m. So temperature is equal to p squared divided by m. So p squared is roughly m times temperature. So that's why I wrote mt here. And this is a kind of rough argument how this should saturate. And in fact, we can numerically check this thing. So in this plot, the horizontal axis is the temperature, and vertical axis is the thermal ODOC value at t equal infinity, numerically extracted. And different colors means different values for A over R. And now, this looked a really nice linear plot. So we extrapolate, we look at the slope of this, and this is a plot of this slope. The horizontal axis is A over R, and the vertical axis is thermal ODOC asymptotic value divided by temperature. And I plotted it. Then again, it is on a line. So we approximate this as just a line, straight line. And then we arrive at this expression where the thermal ODOC asymptotic value is given by this linear function times this, since this is divided by t, so it has t. And in our calculation, in a numerical calculation, we put this area A to be equal to 1 normalized. So if I reproduce it, then it is proportional to A. So I put A here. Then massaging this equation, in fact, gives you this expression. And this expression is very close to what we suggested. Right? So in fact, we can numerically check this kind of behavior for generic ODOC in quantum billiards. So in this way, the maximum value can be checked. However, we are interested in the exponential growth. So these two are kind of related vaguely. The reason is that, so once you determine this maximum value, then the exponential growth should be around here. So there is an upper limit for the time domain during which this exponential growth happens. So if it reaches the maximal value of the OTOC, then of course, there is no way to go further. So exponential growth should be over there. So there is an upper bound for the time domain of the exponential growth. So in fact, in this stadium billiard case, we found that the LFS time is too short. So even though it may look exponentially growing, the time domain for the exponential growth is too short. So we cannot conclude that it's exponentially growing or not. So that's the conclusion. So what is LFS time? LFS time is defined as a time scale when a particle wave function is delocalized to the whole system. So that's the definition. And more clearly, it is given by this TE, which satisfies this equation. So what is this? So on your right-hand side, you have sigma and L, where L is the Lyapunov exponent. So in this quantum billiard case, in fact, the Lyapunov exponent should be proportional to square root of T. The reason is that Lyapunov exponent is actually measuring how the initial sensitivity grows exponentially. And in classical billiard, there is only one chance to actually change the sensitivity. That is when the particle actually hits the wall of the stadium billiard, right? So if the velocity is large, then you can hit many, many times. So the Lyapunov growth, Lyapunov exponent is large. If the particle is slow, then you have less opportunity to hit the wall. So Lyapunov exponent is small. So from this simple argument, when you have just a box of a hard wall with no potential, then you can easily argue that the Lyapunov exponent needs to be proportional to the square root of E, which is proportional to velocity. So even with this classical picture, you'll find that in fact, any billiard doesn't have a gravity dual, since the Lyapunov exponent is not proportional to 2 pi t. It's proportional to square root of t. So anyway, using this and substitute this to here, and also evaluation, so rough evaluation of this sigma, the proportionality condition, which is the original size of the wave function, which should be given by thermal de length. Then solving this gives you NFS time is proportional to this expression. And if we substitute t is 400 to this expression, then NFS time is about 0.3, which is very short, very, very short. So this rough argument shows, in fact, that, suppose you have a few dimensional quantum mechanics, which is surrounded by generic walls, hard walls, and there is no potential in between, then you'll never get a gravity dual. And also, you'll never get exponential growth. And numerically speaking, if you look at this small picture, so I'm sorry that I should magnify it. So this is time, and this is thermal OTOC in a log scale. If there is a straight line here, then it's exponentially growing. But if you look at this, then exponential growth ended here, which is a very short time, like 0.01. And that is much smaller than inverse of the Lyapunov exponent. So the time scale is not enough. Time domain is not long enough to judge whether this is exponential growth or not. So this is the conclusion for the quantum billiard. Yeah, please.
Yeah. Could you show us the numerical plot? In the numerical plot, it appears that the time duration for the exponential growth is much shorter than the naive estimate, the
That's
approximate 0.3. Do you have any reason for that?
Yeah, so in fact, we argued this in our paper, and argument is as follows. So there are 2 points. So one is that this evaluation of LMFS time, 0.3, in this plot, it's something around here. So, so in that sense, it's kind of consistent. It grows rapidly, and then around this LMFS time, it saturates to the maximum. Yeah. So that is one observation. And the other one is that it's a generic argument about the wave packet hitting the hard wall. So suppose you have a hard wall like a billiard, and then consider a Gaussian kind of wave packet, and then smash it into onto this wall. Then of course it bounces back, but when it bounces back, then the Gaussian nature of the original wave packet is broken. It is really broken, and it has a wider width. And I think this is the reason why even before estimated LMFS time, the classical picture of a wave packet is broken.
All right, thanks.
So, yeah. Do you see that? So, did I answer your question?
Yeah, I understood that the breakdown of the particle, the breakdown of the point particle approximation occurs far much earlier than LMFS time.
Yeah. Okay. Yes. So yes, at the time we argued that billiard is bad because it has a hard wall. So if I replace it with some soft wall, then it slowly bounces back with a particle picture.
Even when you have that kind of soft wall, the Gaussian structure will be destroyed. So
yes.
I guess you would get essentially the same result. Don't you agree?
Yeah. So this is a very nice discussion about the intuitive picture of why we lose a particle picture. But so I'll show you later about this inverted harmonic oscillator, which has a double well potential with a smooth wall. And then there, somehow we can actually see the exponential growth.
Then that example would correspond to imposing a special boundary condition.
Yeah, maybe.
Maintain the Gaussian structure of the wave packet. Maybe.
Yes. Yeah, okay. Maybe. We haven't checked, but what we have checked is that when there is a hard wall, then Gaussian wave packet is completely broken soon. But we can at least argue that when it is soft wall, then how much it is broken is getting softer, probably. Yeah. Some kind of.
All right, thank you very much.
Yeah, thank you for the discussion. Okay, so remaining 10 minutes, so this is the conclusion. We have confirmed this picture. There is no scrambling for quantum billiard, unfortunately. And classical Lyapunov is always proportional to square root of E, which is square root of T. So there is no way to have billiard as having a gravity dual. So our target is to have some examples with scrambling, which has a chaotic picture, and the other one doesn't have a chaotic picture. So let's go to the later 2 examples. So here I have 5 slides. So let me argue first coupled harmonic oscillators. And that detects actually phases of the classical chaos. And we go to inverted harmonic oscillators. This is one-dimensional system, so there is no classical chaos. However, it shows scrambling. And finally, I'll show you a general theorem about Lyapunov bound in one-dimensional quantum mechanics, which has some nice indication. Okay, so in coupled harmonic oscillator system, we use this kind of Hamiltonian. So it is a two-dimensional system. It has a mass term for x and y coordinates, and there is a coupling in between x and y. Of course, without this coupling, the Hamiltonian is completely integrable. It's just independent two harmonic oscillators. But because of this, there is a chaos. And in fact, if you look at classical Poincare sections of this classical system, then at low energy, the orbits are regular. However, if you increase the energy like this, and this, then at higher energies, it becomes chaotic. So there is a phase transition between regular phase and chaotic phase. And when you measure the classical Lyapunov exponent, then in fact you can easily see the phase transition. At energy smaller than a certain value, it is 0. Lyapunov exponent is 0. However, if you turn on energy above the certain value, then it becomes non-zero. And at high energy, by using a very nice scaling argument, you can show that the Lyapunov exponent is proportional to e to the 1/4. So if this classical Lyapunov exponent is realized in quantum systems, then quantum Lyapunov exponent is e to the 1/4. It doesn't agree with 2 pi t. So this means that there is no gravity dual. However, there are subtlety when you go to quantum systems, so we cannot conclude in that way quite soon. So let me show you the coupled harmonic oscillator results. So here is a result for thermal OTOC. And there is a saturation behavior around here as expected. And you can also check that this is consistent with p squared, x squared, as we said before. And the important part is around here. So in fact, this is a log plot. So the linear growth around here is the exponential growth. And exponential growth has a nice long duration. In particular for t is 5, it gets longer. And then you can actually extract the quantum Lyapunov exponent of this thermal OTOC. And the result is this. So the horizontal axis is temperature, vertical axis is OTOC quantum Lyapunov exponent. And they are non-zero at higher temperature. But at lower temperature, as you see, for example, for temperature equal to 1, there is no exponential growth like temperature equal to 5. So you cannot say that this is exponentially growing. So around here, there is no plot. But at a higher temperature, there is exponential growth. And you can see that in fact, the exponent, Lyapunov exponent is proportional to t to the power of c, where c is almost like 1/4. So at this stage, we can say that this does not allow a gravity dual since it does not have a horizon behavior. But anyway, the lesson from here is that this system has phase transition at lower temperature or lower energy, it is regular. At high temperature or high energy, it is chaotic. And OTOC actually can discriminate these two. So here is a summary about this coupled harmonic oscillator system. So for classical analysis, at low energy, it's regular. At high energy, it's chaotic. However, in between, there is a mixed phase. In Poincare sections, there is a mixture of regular orbits plus scattered plots. So there is a mixed phase. And this mixed phase will be almost eliminated around temperature 4 or 5, as you can see from the Poincare sections. This one. So for example, around here, you have very little number of regular orbits. But here, at lower temperatures, there are still some regular orbits, but here scattered. So in this sense, if you look at Poincare sections, then there is a mixed phase here. And what about the quantum result? So we looked at thermal ODOC. Then for lower temperature, the system is oscillatory, but at higher temperature, there is an exponential growth. So this is completely corresponding to the indication of this classical chaotic behavior, fortunately. And one important comment is that, so normally when you say the system is quantum chaotic, you look at the level statistics, energy level statistics. And the energy level statistics, if it is Wigner, then you say that it's quantum chaotic. So you can do the analysis for this system. And then it turns out that the Wigner behavior can be seen at very, very high temperature or energy. So this means that at lower temperature, if you look at only level statistics, then you cannot find chaos. You have to go to very high energy. On the other hand, if you look at ODOC, then exponential growth can be seen at a very reasonable value of the temperature, and that is consistent with the classical chaos. So this is one point which we got as a lesson.
Koji?
Yeah, please.
Yeah, I have some technical question. In your left upper plot for the thermal OTOC, in order to read off the exponential behavior, what was your time range? It's between 2 and 4?
Oh, I see. Thank you for the question. So in this picture, the question is where I should look at for the exponential growth, right?
Yeah.
So it is from, for example, the bottom here, 1 to something around here. Yeah.
But it seems it's quite wiggly.
Around here, right?
Yeah.
But yeah, so this time range need to be bigger than the inverse of Lyapunov exponent, right?
Yes.
Since it is exponential of Lyapunov times t. So if you want to say that this is exponential, then it should be larger than inverse of Lyapunov exponent.
Yes.
And when you see the Lyapunov exponent, it is about, this is the value. So it is about 1/4.
Right? I see.
So the value is around 4, I think. So you have to wait 4 seconds to see whether it's exponential growth or not.
Yeah. Just that it does not look like an exponential.
Oh, you're right. So yeah. So the criteria is that from here to around here, so it is about 4 seconds. So you would be, roughly say that this is exponential. But that's it. Yeah, there is no stronger criteria about it. Yeah.
Okay, thank you.
Koji, I have another question.
Yeah, please.
This is for, these results are for, so I'm just looking at the bottom part of your slide here. These results are for fixed coupling. So you've picked the coupling in your Hamiltonian as 1/10, right?
That's right.
Do you know how these boundaries change as you change the coupling?
No. It's a very good point. So suppose I dial this coupling constant to smaller values, then chaos shows up only at very high temperature or high energy, because the coupling gives you the chaotic nature. Right? So in that sense, for this model, the dialing the coupling constant would change, for example, this vertical line or this line to the horizontal direction. It changes. Yeah, however, I think that naively speaking, we haven't checked it, but naively speaking, dialing this coupling constant doesn't change the whole phase diagram here. Yeah, that's what we believe.
Okay. So qualitatively, you expect it to look the same.
Yeah.
Okay, just with shifted boundaries.
Yeah.
Okay,
for this
good.
model.
Thank you.
But for the other model, which is inverted harmonic oscillator, I think the situation is a bit different. So I'm going to tell you about that.
Great.
So I'm sorry that I run up 1 hour, but would you give me 5 more minutes?
Actually, I meant to tell you at the beginning of the talk, our seminars don't really have a time limit. You can go.
Thank you very much.
Going.
Thank you. Thank you. So yeah, I'll finish in like five minutes. So so final example is this inverted harmonic oscillator, which is in collaboration with Kunyon and Ryota and Kyombo. So as you see, the potential shape is this double wall potential. And with this chosen coupling constant G, which is 1/50, then the quantum energy levels look like this. And this lambda, which is a parameter here, actually gives you a classical Lyapunov exponent around this top of the potential. So lambda equals 2 means that if you put a particle here, then the sensitivity to the initial condition is just given by Lyapunov exponent, which is equal to 2. And compared with Jeff's and his collaborators' work, we put this softball so that all the energy levels are completely quantized, so that it looks like a bounded system in classically. So we can define classical chaos too. And energy eigenvalues are like this. And since this is one-dimensional system, a one-dimensional system has very tiny dimensions for the phase space. So classically, there is no chaos. Okay, the result is here. The thermal OTOC is plotted here with the log scale, the vertical axis, with as a function of time. At lower temperature, it is really periodic, since quantum mechanically at low energy levels, the particles actually goes on this classically harmonic oscillator potential at the bottom. But when you increase the temperature, then you can include the higher energy effect. And then at one point, it starts growing exponentially. And in fact, so these dashed parts are irrelevant. However, these solid parts are the ones which we use to extract the Lyapunov exponent. And the plot of the Lyapunov exponent is here. As a function of temperature, it becomes non-zero around temperature equal to 5 or so. And then it grows a little bit. Then it goes down, and it may go to some constant. This constant is non-zero. If I fit this behavior, the high temperature behavior, numerically obtained by this function, constant plus 1 over temperature, then this constant part is non-zero. So it asymptotes to non-zero constant.
Koji, I have a question.
Yeah, please.
Yeah, so in this first plot in the thermal OTOC, so this different temperature lines here. So is this all? Is this so there is an initial dip here? Is it universal for? Is it for any lambda, or is it for certain lambdas? This dip that you initially get, there's like a.
So I think this is universal at least for lower temperatures. As you can see, for example, around here, so the lowest temperature case, T is 1, and it is almost periodic. And this is, in fact, the behavior of harmonic oscillator.
But does it depend on your lambda at all? Like.
Oh, I see. So lambda is this curvature.
Yeah,
right?
yeah.
So it would depend whether we fix G or we fix the curvature here. I think generically it would depend on lambda. For example, if I change lambda in this with G fixed, then you can change the height of this potential barrier. Right?
Yeah.
And if you change it, then I think the temperature is something like if you increase the temperature, then you can include this effect or not, right? At low temperature, you cannot include this top of the hill effect. But if you go higher temperature, then you always include this thing. So it means that when you change the height of this potential barrier, then the time scale of having this exponential, so temperature scale of having this exponential growth would be different.
I mean, I'm saying, I mean, I understand that this is all for certain lambda where this is inverted, but even within the inverted regime, is this generic that you will get a dip for all those lambdas that gives you an inverted?
I think I have to check my results.
Okay.
I'm not sure since so temperature 30, the dip is smaller, and we have a data until temperature 70. So yeah, this dip would be much smaller. However, it could exist. So why are you concerned with that?
No, because we had a paper recently out with Jeff and other collaborators. So we did plot the complexity, and we found that the scrambling regime that we call it, like when the complexity was more or less flat and then it grows linearly, almost linearly. So in that flat portion, previously we found that for wave function, if you compute the complexity from the wave function description, then you almost get, it looks almost like flat. If you're in a log plot, you can see that there's an exponential growth, but it's almost like flat in the regular plot. But then for operator description, we see a dip for a certain choice of the operator, and I don't know exactly what physically that means. And it looks like there you have a similar feature here. So I was trying to see if there's any connection.
So I have a question about that. So in the case of complexity, if you consider a free field theory or just harmonic oscillator, not inverted, just
we had an inverted harmonic oscillator. That was not really a field theory.
Sure. Yeah. But if I use the usual harmonic oscillator, then complexity actually goes down first. It shouldn't go down, right? By definition.
Right. So that was actually confusing to us too. So certain parameters, we found there's a dip, and which like in other methods of complexity, we never found. So we basically use this new technique, this Heisenberg operator, the operator method by using this Heisenberg group. And we for a certain choice of the parameter, there was a dip. And I honestly don't know the physical meaning. That's I've been struggling with that. So that's
nice.
I don't know the meaning of that. Yeah.
Nice. So here, I think so this dip is caused by this standard harmonic oscillator, right? So since it goes down first, and if you have a very low temperature, then this behavior should be dominated by this just cosine function. So that's why we have a dip here, right? Yeah. Other than that, I have no idea. So some OTOC can decrease. However, complexity cannot. Right?
I mean, it can decrease. We have another work where we have seen that if you look at the cosmological evolution, and at the beginning, when you are in the accelerating phase, you see a growth of complexity, like the usual one that you see, and it indicates chaotic-like behavior because the Lyapunov of the slope of the linear growth portion looks like bounded by, not bounded. We cannot exactly precisely pinpoint the bound, but we can claim that this is roughly goes as the Hubble, which essentially is the temperature scale, right? So we have a similarity there, but then when this universe enters into the radiation regime, then we see some sort of decomplexification. So and this is precisely because you are starting with a Barnes-Davis vacuum, right? And then you're looking at the evolution and you're basically plotting it piecewise. But I think if you look at the radiation regime directly from some deviation from the Barnes-Davis already, then you might not see that decay, you might see a growth. So effectively it looks like a decomplexification, but I guess that's because of you're looking at your reference, it's because of the choice of the reference state where you're looking at it. So it could in principle be, but it depends on the context, I think.
I see, I see. Yeah, so yeah, it's natural that it, of course, depends on what is the reference state.
Yeah, exactly. So that precisely depends on how you're, yeah, exactly, where you're starting your reference.
Yeah, so here, so maybe that kind of argument also applies to this. So even though I say it's a thermal OTOC, there are many kinds of definitions for thermal OTOC. For example, what kind of choice of the operators, and also whether you insert this thermal partition function in one place or you divide it into 4 places. So depending on that, actually the detailed behavior would be different, right?
Right. Yeah. Can I also ask you another question in this? Since
please.
So I wanted to ask you about your point on. So this recent paper by Ben Yoshida where they argued that not quite recent, like last year, I think, where they argued that if you take a system which is Gaussian system, and then there is no genuine scrambling, and the way they proved that was they studied basically not the regular XP correlators, but the displacement operator, the OTOC from the displacement operator, and then argued that there is no exponential growth there for the displacement operator. What's your stand on that? I mean, how is it? Do you like? I mean, it's definitely. Can that be like one example? Can that be a generic statement about scrambling?
Well, so I think that the generic belief is that for any choice of operators, if you compute OTOC and it grows exponentially, then for the other choice of operators, it should be very similar. So I think that's the generic belief.
However, no, but that's the problem with inverted. Like we checked in our paper with Jeff that for inverted harmonic oscillator, it doesn't really have an exponential growth for the displacement operator, just like Ben Yoshida predicted. They claimed in their paper.
Yeah. So yeah.
But although, but you know for sure that we know for sure that there's an XP, there's a growth, right? So there's something funny going on there. Like there's some sort of operator dependence, which is very weird, but it's there.
Yeah. So so my point is that it's a generic belief, and nobody actually showed that whatever the choice of operator is, it should behave the same, right? So one thing we tried is that since our OTOC, which is XP, is in fact with the commutator, is in fact so if you take h bar goes to 0, then it goes back to the original classical Lyapunov exponent. So that is almost obvious. So that's why we are concentrated on this choice of the operators. But for displacement operators or other kinds of operators, I have in fact no good. No,
I understand. I don't. Yeah, I don't have a full confidence either. So that's why I'm asking. I don't.
Yeah. I think that's a very big problem since displacement operator has a nice property. So and for example, if we are serious about quantum computational complexity calculation, then of course the choice of operator or choice of the reference state or choice of the definition of the state is very important and relevant for the answer.
Right.
So I know that it's very important. However, here in this
it looks like it is also varying for the level of OTOC, right? So I mean, so then the question is, what is the OTOC that you need to compute, right?
Yeah. So so since in these toy model analyses, so what I wanted to make clear is that even though classically chaotic systems, when you quantize it, then scrambling cannot be seen sometimes, right? So to see this classical quantum kind of correspondence, we better have some operator which has a nice classical counterpart. So that's it. Yeah, that's it. So, anyway, I think we have only classical picture in our brain. So, that's very important. So, and what we understand is only harmonic oscillators. So,
that's true. Yeah.
Yeah, using that constraint, and we just look for some suitable, technically computable things. That's it.
Sure, yeah.
I think that's the universal statement here, right?
That's right. Yeah. I'm sorry, I haven't.
No. Thanks so much. Yeah, thanks so
I
much.
don't
Yeah.
have a good.
No, that's okay.
Excuse me,
So, yeah,
can I
please.
ask about the formula for quantum Lyapunov exponent? So it
Mhm.
seems that in the high temperature limit, where large T goes to infinite,
Yes.
it seems that lambda goes to some constant 1.5058.
Yes.
But naively, I expect that in the high energy limit, wave function or particle will be insensitive to the detail of the potential, and the Lyapunov will be washed out. And do you have any explanation why lambda converges to constant?
I think that's a very important point, and I can borrow one argument written in this paper. In fact, in this paper, so there is an argument that there should exist a semi-classical bound about ODOC Lyapunov should be larger than the subtle classical Lyapunov, which is lambda in our case, which is 2 in our case. And our limit shows that it's close to 2, but it violates this bound. So anyway, the answer to your question written in this paper is as follows. So in this picture, suppose I go to high temperature limit. High temperature means that it includes also low energy part with the same weight as the high energy part, right? So if I go to high temperature, then you need to make a summation over all possible energy eigenstates. And now among these energy eigenstates, these are irrelevant to chaos. These are irrelevant to chaos, but these red lines are relevant. And so if you go to high temperature, then it includes high, so chaotic part, scrambling part. And then the discussion is about whether this contribution is small compared to all the others or not, right? So if the portion of this part is small compared to the others, then this will be a kind of disappearing, right? So, however, we know that for this scrambling energy eigenvalues, the OTOC is exponentially growing. And for the others, it does not grow exponentially. So this means that once you include this part, then it becomes dominant. So that's the reason why at very high temperature, it should exponentially grow, and it is dictated by this. And that sounds very plausible, right? So in this paper, they argued something like that. They have a little bit more detailed argument about how you H bar goes to zero limit and discretize the phase space and evaluate the volume of this exponential growth compared to the other volumes. And so, but the argument is still sloppy. So in that sense, I think their argument is still conjecture. But they claim that they prove this bound, semi-classical bound of this due to that argument. The high temperature limit gives you this classical saddle. That's the argument. So thank you. So the reason why this number is smaller than this number is that their argument is for H bar goes to zero limit. But in our argument, we are still H bar finite. So in this potential, if I take a limit of bringing this potential here to higher and higher, then it corresponds to classical limit. Then in that limit, maybe this bound may be true. But in our case, still we have a very discretized structure of this. So that's why we violate this bound.
can you also explain other features you can find from this fitting formula? For example, so you have 1 over t dependence converging to a constant, and also you have turnover around large t is around n.
Yes.
Is there any information you can get from those features?
Actually, no. The reason is that so in fact in our paper we have also considered a different system with hard wall. So I was concerned very much about the hard wall. So I replaced this soft wall by a hard wall and then do the same computation. Then the result is that it does not go from above, it goes from below. Yeah, so depending on, so first of all, we could see the exponential growth even with the hard wall. So that was somehow good for us. But if you plot it, then yeah, the approach was different. So we tentatively conclude that this behavior is not really physically understandable immediately, but asymptotic constant would be kind of this bound. Yeah. So yeah, thank you for the question. That's a very subtle part, and I want to have some good idea about that.
Thank you very much.
Thank you. So time is almost 20 minutes, but here let me introduce one theorem which sounds nice. Lyapunov, quantum Lyapunov bound in generic one-dimensional quantum mechanics. So we have a theorem stating that in generic one-dimensional quantum system, which has of course no classical chaos, the scrambling occurs because we have an imparted potential, a harmonic type potential. The Lyapunov obeys this equation. Lambda is smaller than some constant times temperature. The proof is quite easy. So first of all, to probe the potential top, you need energy which is larger than the top of the potential. And also, if you want to probe here, then you need a nice wave function which can resolve this structure. So you need to see the bump by the wave function. And that gives you the condition like this, where delta x is the size of this bump. Then the temperature needs to be bigger than this one and also that one. And when you consider this kind of potential, then V top and delta x is given by lambda and g like this. And temperature is given, should be larger than this and this to probe this top. And then you compute this, then you can say, you can prove this bound. So in this way, in generic quantum mechanics, in fact, Lyapunov should obey this bound, which really looks similar to Mauthausen Stanford-Schenker's bound. So here is a conclusion. So I think we had a nice discussion with all of you. So this scrambling versus chaos, this table can be filled in any way, even for one-dimensional or two-dimensional one-particle quantum mechanics. So we have to be very careful about the distinction of these two. And also scrambling, which is an indication of having a gravity dual, can be made even with the simplest inverted harmonic oscillator. Of course, the temperature dependence is different. So this is not actually a generic way to get gravity dual. However, we have to be careful even when we have a scrambling, it may be just made by inverted harmonic potential without any chaos. Okay, thank you very much for listening.
Thank you very much for the very nice talk. So I have one question about the statement as to whether or not there's a gravity dual if there's scrambling. Mm-hmm. Are you saying that the reason for that is that you know that the scrambling time of the black hole roughly goes like 1 over t log t or something like this, right? Mm-hmm. Mm-hmm. Corresponds to a Lyapunov exponent of 2 pi times the temperature, so as in it saturates the bound. Is that roughly the argument?
I think it's not. So I have no good idea of how to relate this Lyapunov exponent with the scrambling time itself. So if any of you have a kind of a nice argument for relating these two without using black hole, then that would be great for me. So what I mean by having a gravity dual is just by the Lyapunov exponent, since as I showed you very briefly, the exponential growth rate is given by the surface gravity of the horizon, which is 2 pi t, right? So, and on the other hand, the scrambling time means that you have a sphere-shaped horizon, and then once you perturb the horizon, then it propagates to the whole black hole horizon in this scrambling time, right? So
you had a formula for the Ehrenfest time up before.
That's right.
And it looks like that if you had like that would equal this, if that equals the scrambling time, right? So if your capital L goes like t, then this would roughly equal the scrambling time of the black hole, right? Is that right?
Yeah, that's right. Well, although I'm not sure about this power, in fact. So yeah, I have to check it, but yeah, it is certainly log of, yeah. But here, do you think the argument is actually Ehrenfest time times is equal to scrambling time?
Yeah, that's what I was roughly asking, if that's the argument you were making as to why these things need to be.
No, in fact, yeah, in fact, I haven't meant it. So here, so this argument about the Ehrenfest time here is only for showing that in this stadium billiard case, the Ehrenfest time is too short. So there is no way to actually pick up the exponential growth in OTOC. So only for that purpose I presented it. Yeah. But,
so Koji, let me ask you a related question. So your definition on this slide of what the Ehrenfest time is, the time scale along which the time scale at which the particle wave function is delocalized over the whole system size.
Well, that's I think the real question. So scrambling is usually defined with many body systems. So suppose you have a large N system, and then you excite one particle, then it propagates to the whole system, right?
That's right.
And yeah, once you have a many body quantum wave function, then I think you can define scrambling time in that way, since you can actually excite one particle among N.
That's
but
right.
Here, since I have one particle, so if I excite it, of course, yeah, it excites all, right? So the usual notion of scrambling time is not present here. I think that's the point. So, as you see here, Ehrenfest time can be defined, of course, since even one particle you can localize it. Then this localized one can spread to fill the whole space, right? And yeah, in that sense, it would sound similar to scrambling time. Yeah.
Maybe we can make it more precise. I mean, so another way I would think of the Ehrenfest time is if you Fourier transform, then the wave function being delocalized tells me that in Fourier space something's getting localized up until it gets delta function support somewhere. So I wonder if that could be used to make, because in Fourier space I can think of taking the wave function. Okay, not even Fourier space. I can think of taking the wave function and making an expansion over modes. In which case, the delocalization of the wave function is distributed over those modes. In the same way that I would guess scrambling takes a single particle excitation in an n-body system and then distributes it over distributes it over all the degrees of freedom of the system.
I see, I see. So you replace these n degrees of freedom by having several energy eigenstates and then
Something
spreading
like that, yeah.
among. I see.
I mean,
Yeah,
if there's a difference, then I guess the point comes to, is there a difference between the wave function delocalization for a single particle system and scrambling in a many body system? Yeah.
Yeah, I think that's a good idea of generalizing the definition of scrambling to few body systems. Yeah, I think following your argument, suppose I have a many body system, then exciting one particle means that so you have many systems and energies are actually given by the symmetry property of those n particles. And so if you think of them as a degenerate energy eigenstates, when you consider a classical picture of that, then it means that you perturb one of them, and then whether it time evolves to spreading of all of those energy eigenstates, they look very similar to what you suggested. So yeah, so even for one body system like mine, there would be a proper way to define scrambling time, yes. But for that purpose, I think our starting point, which is micro-canonical energy eigenstate, is bad, because if you stay there, then you stay there forever. So some strange thing like perturbation or some superposition of wave functions, maybe necessary.
I think it should be something similar to the Ehrenfest time, maybe not exactly the same thing. I mean, roughly, if you think, okay, you have a many-body system, and you can compute the OTOC, and then your OTOC will look like e to the power some Lyapunov times time, right? And you can have a spectrum, for instance, the Lyapunov spectrum, right? And you can have, if you wait certain time, then you can, that could be, roughly speaking, e to the power some lambda, like the largest Lyapunov time, right? So in that sense, and if you demand that there's an analog, there should be an analog of the black hole. Let's say the field theory has a gravity description, right? So if there's an analog you demand, then there should be some analog of that as well, right? And that that should look like something like e to the power lambda t as well, right? In the same spirit.
Yeah, that's right. Yeah.
So now if you reduce the system to one body, then there should be an analog description. So my expectation would be something very similar structurally, I think, the scrambling.
I see. Yeah, I think that argument is very important in a sense that it can provide another good criterion for discriminating gravity dual. So one argument I can do is that although we could start with any body system, if I can actually pick up 1 degree of freedom and integrate out others, then still this exponential growth can be seen, right, for this one body system.
Right. Yeah.
And if that is true, then I think exponent is actually a clear criterion. However, scrambling time, originally I thought that you need at least 2 particles to define it, scrambling time. And so I'm not sure whether this scrambling time notion can survive after integrating all the.
Yeah, I agree. I mean, it's certainly makes sense with an open system.
Yeah, it's a very important question. Yeah, I want to find one at least some good example of having just 1 degree of freedom, which allows gravity dual. But I'm not sure. So for example, if I start with the BFSS matrix model, n by n, and then use one D0 brane as a probe, and then integrate out all the matrix degrees of freedom, which is like a Izuka-Polchinski model. And normally people argue in area safety context that this one particle actually probes the gravitational potential near the black hole or far away from the black hole. So I think that kind of picture should go through this OTOC computation. And if that goes well, then this kind of one-body system analysis would be a good playground for having a gravity, so checking whether there is a gravity dual or not. However, if this integration out actually demolishes everything, then yeah, of course, we just hope that it should go well. So yeah, that kind of argument is important for the discussion about scrambling time, I think. Yeah. So thank you very much for the questions.
Thank you for taking time away from dinner to talk to us.
No. You need to have lunch, right?
We really appreciate the talk. It was a wonderful talk. I've been meaning to hear you talk about these things for a long time now. So thank you very much. Appreciate it.
Thank you very much. Thank you.
Great.
Thank you.
So Koji, our talks are recorded, and if it's okay with you, we will put it up on our YouTube channel.
Sure,
as well.
sure, please. Yeah, please.
Great.
Thank you very much.
So I think Nathan will send you a link as soon as it's available.
Okay, thank you very much.
All right.
Thank you so much.